Hello, everyone. Uh, I hope you're doing well, and thank you so much for attending in my seminar. Today, I'm gonna present LAMP, which includes some new approaches to make mixed network more efficient in terms of latency. And then it tries to provide these approaches in a way that they will be used in practice. So at the beginning, I'm trying to provide some introduction to make sure we are on the same page. So I'm gonna brief on the necessity of using anonymous communication network like mixed network. And then we will see as a result of using such systems, the quality of service on internet will be degraded for clients. And then eventually I'm gonna introduce LAMP, with help of which we can improve the quality of service on internet while using the anonymous communication systems. Okay, so as you know, by default on internet, when two endpoints want to communicate, their communication will be secured using encryption schemes. But the fact that these two endpoints are communicating usually is not protected or hidden from the perspective of a network adversary observing this scenario. And it actually can be problematic because it will raise some privacy issues that we need to address. To address such issues, one of the typical choices is to use Tor network. Tor network is an overlay network on internet, consists of some relays that are known as Tor relays, and usually we categorize them as guard, middle, and exit relay. And in this network, if a client wants to have some sort of anonymity, can pick one guard, middle, and exit relay, and then, she will exchange some keys with these relays and tries to encrypt her packets with the key that has been exchanged with the exit, middle, and guard relays respectively. And then forward the messages through this path. And in this path, each relay will receive the messages and will, peel off one layer of encryption and knows the succeeding relay to forward the message to. And this process will be continuous until the message is received by the destination. So in this network, as long as these Tor relays are not collaborating, or more accurately, as long as the guard and exit relay are not owned by one entity, we can say we have the client destination anonymized. But with the assumption, with the very important assumption, that the internet service provider who observes the communication from the client to the guard is not as the same as the one who owns the network between the exit to the destination. So, as you might guess, if these two internet service providers are the same, then we will have a big problem. Why? Because the internet service provider actually can collect the data regarding the packets the client is sending to the guard relay, and also he can gather the packets that are being sent to the destination from both ends of the Tor network. And then he will apply some correlation attack based on some machine learning techniques, and unfortunately with high accuracy, he will be able to say who communicates with whom. So the connection will be de-anonymized. So then we need to actually provide stronger techniques to avoid such adversarial behavior. To do so, first we need to have a good understanding of Mixnet, which is an entity on internet receiving traffic for different sources, and it will shuffle this traffic and delay them before sending them out. And in this scenario, if you consider the network adversary or the internet service provider, for that actually internet service provider, it would be really hard to connect or map the input of the mixnet to the output. So somehow, we can degrade such attacks. If I want to be more specific, usually we use mixed nodes together with other mixed nodes, and we construct a network that is known as mixed network. Normally, we consider like a layered format for this network, which we classify the mixed nodes in some layers, and each layer would be a mixing layer for us. And in this scenario, client, kind of similar to Tor, will pick one node from each layer to make a communication path to the destination. And interestingly, now the internet service provider can corrupt whatever he wants. He can just observe all the communication link on the internet. And still he can not have any clue of the communicating parties. Then the client destination will be perfectly anonymized. Even we can be more critical. We can consider a scenario that this adversarial behavior will be extended to the mixed node. So the adversary actually can corrupt some mixed nodes. And then for those mixed nodes, he can see what happens, how to map the input to the output. But even in this scenario, as long as one mixed node is acting honestly, we can consider the anonymity of the client to the destination preserved. So that's great because we had a privacy issue on internet regarding the anonymity of endpoints, and using mixed network we can perfectly address that. But we should note that in mixed network we achieve this high anonymity at the cost of very high latency. So latency in mixed network is high because of two key reasons. The first reason is that the client, instead of forwarding the messages directly to the destination, is trying to pick out some intermediary nodes through which it will, transmit the packets. So these intermediary nodes can be really far from each other, right? So it can be like a high latency distance between them, so it will cause a high end-to-end latency. Not to mention that the second reason is that each node has been supposed to provide some mixing or shuffling process. This mixing always is coupled with some delay, and it will further contribute to high end-to-end latency. And it's actually really bad because some clients might adopt mixed network for instant messaging or web browsing. But currently the mixed network is not ready to be used for such purposes because the latency is very high and it would be impossible to use it. And it limits the application of mixed network. So now a good question is that, okay, so what we should do, and if there is any research that has been discovered that try to discover some solution for this problem. To discover that, I'm gonna briefly introduce LARMix, which is the first paper we published last year that we try to identify this issue and we propose some solutions for that. So if I want to be more specific, in LARMix, we try to suggest some clustering methods for clustering the nodes at the beginning. Because if you remember, we have some mixed nodes and we want to design a mixed network that, for example, in our case, it was in layered format. Before doing that, in LARMix, we propose that let's cluster all the nodes. For instance, in this example, we cluster the nodes in a way that some cluster are in Asia and Africa, another one is in America. And then, considering these clusters, in LARMix we propose some diversification algorithm that help us to make sure that mixing layers are geographical, actually they have nodes with diverse geographical location. So that means, for instance, in each layer, we have at least one node from each cluster, like the design you see there. And it would be helpful because if we consider this, then a client, for instance, can forward her packets through a specific cluster nodes, like for example, yellow, green, or red cluster. Or for example, she can try to use nodes that are from the cluster that are close to each other. So in this case, we can lower the end-to-end latency. That was like the main proposal of the LARMix. On top of that, LARMix introduced that this strategic routing, this low latency routing, might cause some issues because before, client has been supposed to use uniformly random nodes from mixing layer. It's just default mixed network. But now the client is trying to bias the route selection. And it can be problematic in a sense that in succeeding layers, we might have some nodes that they receive higher portion of traffic than normal. And in such cases, these nodes might drop the messages and the client will have to send it again and again to make sure that the receiver will receive it. And it inadvertently will contribute to high end-to-end latency. So it's kind of not good. And in LARMix, eventually, to solve this issue, some load balancing algorithm have been proposed to make sure that the client, after applying these low latency routing strategies to go, for example, through the yellow clusters, they can also run some algorithms to adapt their strategy a little bit to make sure that the nodes in succeeding layers will receive more or less the same amount of traffic. So it means that we have the bias routing, also a balanced network. For instance, in this figure, like in the right side, you can see that we have 3 types of traffic: low, moderate, and high traffic rate. And in succeeding layers, more or less the nodes receive the same amount of traffic. And then we have like a balanced network. So LARMix really proposed these approaches to make a trade-off between anonymity and latency. And it has been shown to be effective. It really reduced the latency. And which is nice, but we were wondering that if we can really adopt these approaches in practice or not. So we tried to perform some experiments after we had this LARMix paper. We realized that actually there is a huge problem. The LARMix impose a very high computational cost, which can be in order of n to the power of 5. When n is the number of nodes in the network, which usually is in order of thousands, so it can be really costly to implement LARMix in practice. So that is really a big problem. And apart from that, we understood that it's very nice that LARMix provided this clustering and diversification scenarios to make sure we have diversified nodes in the mixed network. But we realized that it contributes little in terms of improving the latency while providing very high computational cost. And we tried to provide some analysis and really realized that, we can just cut off this clustering and diversification. And maybe we just make sure that we introduce nodes from different geographic location available in mixnet pool before selecting the node to arrange the mixed network. And it turned out to be good enough for us. So we realized that then we can just cut off these 2 processes. Apart from that, we realized that this is really nice that LARMix provided this load balancing algorithm. I don't know if I'm audible or not. I hope I am. So this load balancing algorithm is really nice. Basically, it will be helpful to provide a balanced network, right? But then the issue is that we need to make sure the client will apply this load balancing. If client does not do that, so you cannot do anything. You cannot ensure that you have a balanced mixed network. And we have a lot of clients. How you want to make sure that all of them will implement this approach? That was another thing was really subtle that we identified in LARMix proposal that can be probably somehow cut off. And eventually we realized that in LARMix, as a result of using this load balancing technique, the first node will be selected uniformly at random, and it also, contributes somehow to high end-to-end latency. And considering all these aspects, we just came to this point that if we can do better, and it turned out that we can do better, and we proposed LAMP, which includes some lightweight approaches to provide low latency routing in mixed network. Specifically in LAMP, we try to, stick to the fact that this approach should be able to be adopted in real network. That was the main goal that we had. And in general, we proposed 3 different approaches in LAMP, that first of which is single circle. You will see that how lightweight it looks when I'm explaining. So in LAMP, we say that, okay, the node will be assigned uniformly at random to the mixing layer. We don't have any arrangement structure that we like LARMix. And we also don't have load balancing. Instead, we assume that the nodes are high quality, that they can handle even some high traffic rates. This is the assumption that we have. But instead, we are trying to work on the low latency routing. We say that in single circle approach, we consider a client who has access to the information of mixed node in the network, and she wants to select some nodes to have fast connection. To do this client at the beginning requires to select a threshold in terms of latency. For example, this threshold can be 10 milliseconds, 20 milliseconds. Then client needs to examine all the nodes to see if they are within this threshold or not. If they are within this threshold, for the simplicity, we can assume that the client will create a circle around herself and put the node within the threshold inside the circle. And then client will stick to those nodes for message routes in a way that, for example, client will say, okay, I exclude all the nodes that are not within the threshold, and from these nodes, I will choose these 3 paths. She can even have a specific strategy for node selection within the circles. It turned out that single circle actually is super efficient, almost in order of n or sometime n log n when we want to implement it. It's really efficient. And also, this approach can provide some moderate latency reduction, which is nice. We can slightly improve this approach and have the multiple circle approach, where again the client will select the threshold value in terms of latency. But in this scenario, the client will just look at the nodes in the first layer. Let's imagine that the red nodes have been supposed in the first layer of Mixnet. The client will make a threshold circuit, like a circle, and try to pick out the nodes that are within this threshold. And then eventually, the client will make a selection out of those nodes to be in the first layer. After this, the client will again consider that threshold, but this time from the previously chosen nodes. She will measure the latency from the previously chosen node to all available nodes in the succeeding layer and try to, filter them and finally pick out one node which provides reasonable latency. And eventually it can, the client can do it again for the third layer and so on to have a end-to-end path. We realized that multiple circle actually is efficient, maybe slightly less efficient than single circle because you need to have few circles and few measurements. But the thing is that it can provide really dramatic reduction in end-to-end latency. Eventually, we provided the third approach, known as regional mixnet. So in this approach, we consider the words. We say, okay, this is the word, let's partition that. And each partition can be a region. And then we're gonna build up a mixed network in each region. Then the client of each specific region should stick to using their mixed network. So in this way, again, we are excluding some nodes, but this approach is very efficient because each node can be either in region 1 or region 2 in this, for example. So it's really easy to classify them. You don't need to run any algorithm for that, which is a nice thing. And on top of that, it can provide like very good amount of reduction in end-to-end latency. Okay, so great. I have talked about LARMix and LAMP at a very high level. Maybe now we need to like look at some metric that can help us to compare these two approaches. To do so, we should consider like anonymity and latency in mixed network, because the main goal of using mixed network is to have high anonymity. If you are trying to introduce some bias in the network, we should always be careful that we are not damaging the anonymity. And on the other hand, we should measure the latency, because latency reduction is important for us, right? So for the anonymity, we assume that we have that network adversary that at the beginning I mentioned, like the internet service provider observing everything. And this actually network adversary can potentially sample some messages entering the mixed network. And specifically, he can say, okay, I want to look at this specific message going to this specific mixed node in the first layer. And I'm gonna see with what probability this message comes out from one of the mixed node in the last layer. Because if I know that, then I can also find the destination, because I have the full view of the network and I can de-anonymize it. And in this process, you know, the adversary will be able to find a probability distribution mapping the input node to any of the output nodes. And the entropy of that distribution will serve as an anonymity metric for us. So the intuition behind is that you can remember that in like default mixed network, the user was choosing the nodes uniformly at random. And when everything is uniformly at random, it means that the chance of this, for example, message coming out from one of the nodes in 1 over the number of nodes in the last layer. And it means that we have the highest entropy. But the thing is that when we are excluding some nodes, this entropy would be reduced. And that's why this metric is really critical and useful for us. Besides this, to measure the latency, we can like easily consider each client and the possible paths they can make. For example, in this scenario, the client can just make 4 paths considering the nodes, for example, the client has in her circle. And for each path, we can easily now measure the latency and the probability of the path selection. And having these 2 elements can help us to like average the latency and compare them. Great. So finally, I can be able to present the main results of LAMP. So we perform many experiments, like really many experiments, but here I'm just gonna show the main result that we achieved through analyzing LAMP and LARMix approaches. So first, we consider the vanilla mixed network. So vanilla mixed network is like is about a network that the user just, you know, like naively will select the nodes, like uniformly at random from each layer, like default mixed network. And in this case, we realize that the latency is actually really high, like it's 150 milliseconds, which is not so good. But the entropy is also as high as possible, because in uniform approach, you can just have the uniform distribution, which is nice and provides high entropy. Then we came to this point that maybe we need to also look at the ratio of entropy over latency, because entropy should be as high as possible and latency as low as possible. Then maybe this ratio would be helpful. And we defined it as gain. And as you can see, for vanilla setting, the gain is not that high. But the good thing about vanilla setting is that the computation overhead is nothing actually. It's like easiest approach that a client can take. Apart from this, we examined LARMix. We realized that LARMix can really reduce latency compared to vanilla approach, like 55% reduction in latency, which is nice. At the cost of losing 2 bits of anonymity, which if you think it can be tolerable, but the gain of the LARMix approach is not that dramatic compared to vanilla. It's good, but it's not that surprising. However, the main downside of LARMix is the computation overhead, which actually in this case is almost 14,000 times worse than vanilla setting. And it can even be higher when you increase the number of nodes in network, which is a bit problematic. So how can you like implement such model in real network? It can be really like problematic. So then we try to also consider the LAM proposal and the approach that we provided. We realized that using single circle can reduce the latency to 52 milliseconds, which is slightly better than LARMix. And also, surprisingly, the entropy is slightly higher than that of LARMix, which is nice and leads to having higher gain. And eventually, the surprising and interesting part of single circuit is that the computational cost is on par with what we have seen in vanilla case, which is really good. Like you don't need to pay that much in terms of computation overhead, and you will reduce the latency while losing a little bit of anonymity, but having higher gain. Similarly, we actually examined multiple circles approach. We realized that multiple circle approach is really crazy. You can like reduce the latency to 20 milliseconds, like 85% of the reduction in latency compared to vanilla approach, while you still can achieve the anonymity on par with what we had in LARMix scenario. And the gain is really high, like almost 5 times more than vanilla case. And the computational cost is slightly higher than vanilla and single circle, but if you think about it, it's still tolerable. It's not that much. And we even checked it with increasing the number of nodes will not change that much compared to vanilla case. Eventually, we also wanted to look at the regional mixnet scenario that we try to partition the words. And specifically considering our datasets, we partitioned the world into two regions, like Europe and North America. And we realized that the regional mixnet also can be really effective for EU. It can like reduce the latency to 80 milliseconds, 80-70% of reduction, while providing anonymity kinda on par with what we have seen in multiple circuit and LARMix. And the gain also is as high as possible and the complexity is tolerable. But the downside was that for North America, unfortunately, the reduction was not that high. So it was like kind of similar to single circle and LARMix at the cost of losing almost 3.5 bits of anonymity, which is kind of concerning, while providing like the moderate gain with computational cost, which is really low. That's the nice part. But it was a bit concerning. And it like urged us to look at the data set. Why with this pattern? This is a bit concerning. And we realized that the reason is that we did not have enough nodes in North America, like current mixed network, like NIM, has a lot of nodes in Europe, which is nice, but in North America, we didn't have that much node. And as a result, we couldn't make good trade-off between latency and anonymity in North America. So this is kind of a warning that if you want to use regional mixnet, you need to make sure that you have enough nodes in each region. That's the part we understood. Yeah, but in general, LAMP provides this tree approach and it can be very helpful for a client who wants to make trade-off. They will have a free hand to choose whatever they want to have the best setting. Yeah, so in a nutshell, we have seen that there is a very critical problem on internet concerning the anonymity of endpoints, and we need to address them. Addressing that can be happen using Tor network, which provides anonymity, but unfortunately it's really vulnerable to the adversary observing both ends of the network. One can definitely choose mixed network, but mixed network has this issue that it will impose a high end-to-end latency for packet transformation, which is not so good for web browsing or instant messaging. We eventually, if you want to have like high anonymity compared to Tor, but we also want to have fast connection, it can be helpful to use LAM, which can reduce the latency up to 80-70%, while providing approaches that is like lightweight and can be used in practice, hopefully. So yeah, that's it. Thank you so much for listening. If you want to try out to run our experiment, just feel free to have access to our GitHub repo. Basically, we perform many experiments. That's because of the time limitation. I couldn't explain all of them. But the good thing is that we got all the available batch in NDSS, so you can be sure that everything can be reproduced. Apart from that, just feel free to visit my webpage if you want to have access to the slides of this talk or the paper. And if you want to stay in touch with me to discuss anything about communication, like anonymous communication network, feel free to connect me through LinkedIn. Thank you very much.